Okay, so um, I think the starting point, like to think about theoretically what's going on with colligative properties, is to recognize that, like a pure solvent, if you think about a pure solvent, it doesn't matter what it is, but we'll just use water because it's something we all are familiar with. Um, you can start to try and think about, like, if I take pure water and I compare it to, let's just say, water with sugar dissolved in it, or salt or whatever, it doesn't matter. Like, let's say that this has 1 molar glucose and that this is just pure water, same temperature, same whatever pressure, etc. We could say, like, what is the, and it's sort of weird to think about it like this because we usually think about terms of like changes in free energy. So maybe that's a way to think about it. Actually, if I take pure water and let's say I dissolve glucose in it, is the free energy the of the 1 molar glucose higher or lower than pure water? Um, yeah, what's the answer here? You might be like, I don't know, you start thinking about these microscopic viewpoints, etc. And those are always good. I like very much encourage you to think about things microscopically and try and understand why that's true. And we can talk about that. But like one way to look at this is like this happens. We know glucose is soluble in water. If that's true, that means that delta G must be negative for this process. Like if this happens spontaneously, if this happens spontaneously, that glucose will spontaneously dissolve in pure water. That means the delta G is negative, which means that the final free energy must be greater than the initial free energy, right? The final state must be larger than the initial state. Um, I guess another way to say it is that the free energy, I should say it this way, the free energy of the final system is lower than the free energy of the initial system. Um, if delta G is negative, then it necessarily means that whatever your final state is will have a lower free energy than whatever its initial state is. Um, and so we know that another way of stating this is that any solution will have a lower free energy than its pure solvent. So getting back to what we talked about originally, which was like, what's the driving force behind all these colligative properties? Why is delta G negative? We know that delta H is generally going to be 0 because delta H of solution is generally close to 0. So that means that it must be entropically driven. And so entropy is driving this, right? Whatever the entropy associated with the crystal for glucose, breaking that up and increasing the energy of that is more favorable for this system than whatever the entropy is associated with restricting the movement a little bit of the water molecules within the solvent. Um, so the entropy of the solution has increased, or the entropy, I shouldn't say the solution, the entropy of this entire system has increased. And so the solution has a lower free energy than the pure solvent does. And then that helps us tie in what's going on with all of the boiling points and things of that nature. So if delta G, let's see, how can we get there? So if delta G, I guess maybe it's intuitive to think about it this way, but if the free energy is lower, I guess the way I would say it is, if the free energy of the system is lower, so if we take if we look at these two things here, oops, if we say that like G solution versus G, let's call it solvent. So if we're saying that this is lower than this, we're saying that the solution is more stable than the pure solvent is, right? Like we've sort of stabilized the solution. The more solute we add to it, the more stable the solution is. And the effect of that is that it doesn't want to, or it makes it more difficult to push it through changes. It makes it more difficult to push it through these phase changes. So if we look at like a phase change diagram, the reason why this is why the boiling point is higher and the freezing point is now lower. If we look at the phase change diagram or whatever, so if this is if the solid lines are the phase change for the pure solvent, whatever, we got solid up here, this is our liquid, and this is the gas down here. When I add some solute to it, what's going to happen is that's going to move, and that's going to move. And you'll notice that the dotted line, so if, let's say, so this yellow portion here, right, I guess the whole yellow portion here, that part has expanded compared to the blue portion that's in the middle. So it's like initially the liquid was stable. It had the free energy of the liquid was such that it was stable across pressures. So over here we have the pressure, and over here we have temperature. It was stable across like this range of pressures and temperatures. As I add solute to it and lower its free energy, you can think of a lowering of the free energy as a stabilization. Now I expand where it can be stable out into lower temperatures as well as higher pressures and higher temperatures, excuse me. Both, I guess both directions really. But I expand sort of the amount that this liquid can take up now expands out into this phase diagram. So the more solute I cram into there, the more stabilized the liquid becomes, in a sense, the solution. And because it becomes more stable, it starts to take up more of the phase diagram. You can kind of think of the opposite, like if there was a way to destabilize it, then you would expect this to kind of shrink and be smaller here, right? The liquid would start to take up less, and the solid and gas would take up more. So changing the free energy of it, you can think of the free energy of the liquid as it expands. It starts to expand into more of the phase diagram. Why don't the solid and gas change at all? It's because when you freeze something, when it finally becomes frozen, the salt is actually excluded from the frozen solid, so it doesn't actually change the free energy of the solid at all. In the gas, it's the same story, right? Once the thing is in gas phase, nothing is really dissolved in it anymore, so that doesn't really change. So those free energies remain the same, they don't change at all. But the liquid, because now you've got something dissolved in it, now it expands out and starts to eat up some of this phase diagram. So all of the properties that we're looking at, they're all kind of the same thing. We're just saying, well, the free energy of the solution is lower, and so the result is it will stay in the solution phase, this sort of liquid phase, through a larger range of pressures and temperatures. So to write that out, solutions are more stable. Yeah, you can think of stability as being like the more stable something is, the harder it is to change, right? Like people who are in like a stable relationship generally don't break up. And so the more stable the relationship is, the less likely they are to break up. And that's essentially what you're doing here. It's like you're taking the liquid and giving it some sort of couples therapy, and now it's, stabilized in the same way that the couple is, and it's less likely to break up, and turn into a gas, or I guess I don't know what the opposite would be for a couple. Maybe they run into each other really fast or something. But anyway, they turn into a solid, and that's essentially what we're looking at with this boiling point, and the boiling point increasing and the freezing point decreasing. And then so the more that you increase it, increasing dissolved solute, it's exactly what you would expect. Greater freezing point depression. Greater boiling point elevation. And of course, this all stems from lower free energy.